Okay, folks, welcome back. I hope you've had a chance to look at the clustered data exercise. And now I'm going to go through the solutions, which are available as a PDF, which is what we're looking at here. But they're also available as a distance project, cluster solutions, which contains the analyses related to these solutions. And it's that I'm going to go through now. So I'll just switch into distance. Yeah. And I'll turn my video off so I've got a bit more screen space. Okay, so let me open the solutions project. It's available as a zip file in the exercises directory. Cluster solutions. There we go. It wants to unpack it somewhere into the exercises folder is fine. Okay, so you can see here there are a number of analyses, and they haven't been run. We didn't run them to save some space in the zip file. So the first thing I want to do is run them. I'm going to run all of them at once. So if we haven't done this before, you can, if I hold the Shift key and just click, I'll select all of them, and then just hit the Run button, and it will queue them up. Here they are, and run them one at a time. So here it is, just going through running them all. Okay, that's then finished. This one finished with warnings. The rest look okay. We'll come back and look at that later. Okay, so the first question was asking you to run that first analysis that had already been created and have a look at the results, and particularly the cluster estimation pages. So if I just open up that analysis details, and it opens automatically on the results tab. I can't resist just quickly going and looking at the detection function, which looks quite nice. If I just go back and look at the QQ plot, that the dots look very close to the line. There's some evidence here of rounding at that distance. There's a few distances that are the same. But overall, if I look at the QQ goodness of fit statistics, they all, p-values, they all look very good. So this is a good fit. Okay, so I will not get distracted and go and look at the cluster size page. So the mean cluster size was 2.25, and the expected cluster size from the regression is 1.89, and the standard errors on these are 0.1 and 0.2, so it's quite a difference there. And indeed, if we look at the regression plot, on the y-axis here is the log of cluster size, which is the default, and on the x-axis is detection probability. So this is high detection probability where we're close to the line. This is low detection probability far from the line. And the regression goes down this way, which gives us an expected cluster size, which is estimated at detection probability of 1, that's lower than the average cluster size. And this is quite typical. So what's probably happening here is that we're missing the smaller clusters at bigger distances where detection probability is lower, but we do still tend to see the bigger clusters, and so this is a classic case of size bias. The expected cluster size is smaller than the mean cluster size because we're missing some of the small groups, and we're missing them particularly at big distances where cluster size, where detection probability is low. Okay, so we have evidence of size bias. If you look at the t-test on the slope of that regression, it's highly statistically significant, which is another indication of size bias. The question 1 also asks us to look at what percentage of variance of the overall density estimate is due to cluster size. And so if we just go and find that, it's under the density estimates global page. We can see that only 7.4% of the total variation is due to the cluster size regression. Most of the variance in the variance contribution comes from encounter rate variation, and that's very typical for a line transect. Okay, so the second question asks us to choose, this is where we're going on now to truncating the data to look at cluster size. So we'll truncate the data separately for cluster size and for detection function estimation. So we need to decide where to truncate the data for cluster size estimation. And what we want to do is, if I just go back into my first analysis and look at the detection function plot, I want to choose a truncation point where I'm seeing everything, because then if I use the average cluster size from within that truncation point, I'm seeing everything. So I'm seeing big clusters and small clusters, so the average cluster size there is reliable. And so I'm going to choose 0.4 because the estimated detection probability is 1 out to about 0.4. So that's what's happened here in this second analysis. If I just open it up and click on the inputs and look at the data filter, you'll see that under Truncation tab, I'm truncating all observations beyond 1.5, which is what I've always done in this analysis. But here, for cluster size, I'm discarding all observations beyond 0.4. And further, if I look at the model definition that's being used here, under cluster size, I can see that all I'm doing is using the mean of the observed clusters. So I'm going to truncate everything beyond 0.4 for cluster size estimation, and then just use the mean of the observed clusters. And so if I look in the results here, just whiz through the detection function stuff, is going to be exactly the same as before. I haven't changed that at all. But under cluster size, now I'm truncating at 0.4, and so there are only 25 samples left of the 80 or something that I had originally, and the mean cluster size there is 0.87. So that's pretty close to the regression estimate that I had in the previous analysis, which was 0.89. The standard error here is 0.18, which is rather higher than the standard error from the regression, which was 0.13. So because I've thrown a bunch of data away here, I'm less certain what the mean is than when I was doing the regression before. And if I look at the contribution to the variances, I can see that cluster size is now making a slightly greater contribution to the overall variance, because I've thrown away a bunch of information in estimating cluster size. So probably that regression approach is better than the approach I'm taking here of additional truncation. Okay, so the third question was looking at post-stratification by cluster size. Now if I just look in the data here, I can see that there is a cluster strat column where cluster sizes of 1 are giving a value of 1, and cluster sizes of 2 are given a value of 2, and cluster sizes of 3 or larger, so 4, 6, 3, are all given a cluster strat of 3. And so back into the analyses now. Let's look at this one first. So what I'm going to do here is I'm going to post-stratify. If I just look in the inputs here, I'm going to post-stratify using that cluster strat column. And in this analysis, I'm fitting a global detection function, but I'm going to do cluster size by stratum. So that's going to be cluster size by this cluster strat column. And if I look at the results now, I've got exactly the same detection function stuff as before, but now I've got 3 different outputs for cluster size. So there's 1, 2, 3. And so that's cluster size for stratum 1, and that's just the clusters of size 1, so the answer is 1 with no variance. Cluster size with stratum 2, post-stratum 2, which is just clusters of size 2, so again no variance. Clusters of size 3, and so this is the cluster stratum 3, so this is clusters of 3, 4, 5, 6, etc. And the average here is 5.81 with some standard error. So what I'm hoping is that there isn't any size bias in clusters of size 3 and above. One way I could look at that is I can create another analysis, which is the one that I think I've got here. Let me just make this a bit bigger. Yep, that one, where it's exactly the same as before, but now if I look under cluster size here, I'm using size bias regression. So what I'm going to do is I'm going to try the regression method within each of those post-stratification strata. So I'm doing cluster size by stratum, as I say here. So if I look at the results under cluster size, here we go. Then, well, I can't really do a regression when there's all ones. So the first stratum just has clusters of size 1, and second stratum just has clusters of size 2. But the third stratum, it does have different clusters in it, and so I can do a regression. Here's the plot of the regression, and you can see the slope of that is still negative. And if I look back, I can see the p-value on the slope is statistically significant. The mean cluster size, this is what I saw before for this post-stratum, is 5.81, but the expected cluster size from the regression is 4.41, so still rather less, and the standard error is fairly small on that. So it looks like I've still got size bias even in these larger clusters. So that's a bit annoying and not something that I'm particularly happy about. what can I do? Well, I guess one thing I can do, I'm saying that the detection function is different at these different cluster sizes. So one thing I could do is I could fit a different detection function in the different strata and then do a size bias regression. So that's what I've done here. Oh, I see that this analysis is run with warnings, so let's see what the warnings are. The warning says parameter 6 at an upper bound. Okay. So what I've done here is I fit, if I just show you in the model definition, no, sorry, it was here, is this time I fit a detection function by stratum. So this is going to fit a different detection function for each of those cluster size strata. So there'll be a different detection function for clusters of size 1, of size 2, and then the larger clusters. That's why I've got 6 parameters now, is I've got a hazard rate for the first stratum, which is clusters of size 1, a hazard rate for the second stratum, which is clusters of size 2, and a hazard rate for the third stratum, which is clusters of 3 and larger. And so the 6th parameter must be something to do with those clusters of size 6. Remember, there are 2 parameters per hazard rate. So I just look at the results. Now I can see I've got detection function 1, detection function 2, detection function 3, and if I look under model fitting for detection function 3, there's parameters 5 and 6, and there's my warning. Parameter 6 is an upper bound. Turns out the upper bound for that parameter is 20. This is the shape parameter of the hazard rate. So when you get a very large value of that and the upper bound, that means that you're getting a wide shoulder and then a steep drop off. And if we just have a look, if we look at the estimated value for that, there we go, it's 20. It's right up against that upper bound. And if we look at the detection function plotted, there it is. So we get a wide shoulder and a steep drop off. Looking at this makes me think I don't have very much data here. If I just go back and look, yes, indeed, 16 observations. So this is really very few observations to fit a detection function to. I wonder how many I had for clusters of size 2. Model fitting, there we go, 33. And the detection function looked like that. And then clusters of size 1 looked like that. Again, that's a very wide shoulder. That's a bit of a strange detection function. And I had 39 observations. So I really don't have that many observations to fit to do this post-stratification where I'm fitting different detection functions for different cluster size strata. Well, just as an academic exercise, I'll show you what to do about that error message. What I'm going to do is I'm going to increase the upper bound for that parameter. I'm not hoping to get anything particularly useful out of this, but I'm just showing you so that you know how to do it if you need to do it. So what I'll do is change the model definition here. Under properties, detection function, constraints, I need to say, okay, there are 6 detection function parameters, 2 for each stratum, and I can ignore all the ones I don't want to change the bounds on, but on this 6th one, the upper bound currently is 20, so I'll just make it maybe 100. If I click OK, it's going to tell me it wants to delete the current results. That's fine. I'll just run again. Okay, I don't have an error message, I don't have a warning message now, and if I go through and look at the 3rd detection function 3 model fitting, there we go. The parameter estimate, so the bound, I can see the bound now is 100, and the parameter estimate there is 30.9, so it's a little bit bigger than 20, it's settled down at 30.9. If I look at the fitted detection function there, it's actually very similar to the way it was before. What I should have done is recorded the P that I got before, so let me just go back and look at what this is. So the estimated average detection probability is 0.813. Let me go back and run this without that change. Set this back to 0. So this is the way it initially ran. The estimated detection probability here is 0.828, so basically almost the same. So changing that bound really hasn't made very much difference, if any, to the results. But all the same, at least you know how to do it now. So I'm not particularly happy with this analysis because the sample sizes in estimating the detection functions here are really, really small. Um, so I'm not confident, particularly confident in using, I'm using the density estimates that come from this. I was just going to look at the cluster size. So there's sort of less evidence of size bias now because we fit a different detection function for the different cluster sizes. So the size bias is sort of partly mitigated by the fact that we fit different detection functions. But my main conclusion here is that with a sample size of 16, I'm really not all that happy fitting different detection functions for different cluster strata. So I guess another option would be to fit cluster size as a covariate in the regression, and we'll talk about that once we talk about multiple covariate distance sampling in a future lecture. But for the minute, I need to decide which of these analyses I'm the most happy with and which I would use. And I think for me the answer is I don't really like this truncation one because I threw a bunch of data away, and because of that I had more variance in the cluster size estimation. I don't necessarily like these post-stratified ones because I wasn't that happy with just using the mean. And if I'm going to use a cluster size regression, then I might as well use a cluster size regression on everything. And if I'm going to fit a different detection function for each post-stratification strata, then I'd want bigger sample sizes. So what I'm left with is the standard regression of cluster size against probability, log of cluster size against probability of detection, I think is the one that I'm most happy with. You can see it does make a bit of a difference to the answer. So 0.49 is the estimate of density from that. Whereas the estimated density with these is not very different with the average cluster size. The CV is just a bit bigger. And then from these post-stratifications, the estimates are looks like about 10 to 20% bigger. But all the same, I think this is the one I'd choose. And in fact, that is the default method in distance. Okay, I'll stop there.